So somebody uploaded to the discussion board some notes that you guys had on the students' tea distribution stuff. And so that means that our packet was right on course for what we wanted to do. Did you talk at all about hypothesis testing yet? Nope. Okay. So that's probably your next topic is my guess. I'm not sure about that. So when I finish this handout, I have some new handouts for you. But the one that we're starting with is from the handout you already got last week, or sorry, last Tuesday. So if you have this stuff from Tuesday, you already have this handout. What we had talked about on Tuesday was that we had this chart that let us determine if we should be using the Z distribution or the T distribution. And that was part of the notes that somebody shared with me as well. So I saw that you got the same chart she gave before. And it said when we start, if we have the population standard deviation, then we go this way, and we're probably going to land on the Z distribution. So the problems that we did on Tuesday, we were using the Z table. Today, we're going to be working on things where we don't have the population standard deviation, and instead we just have a sample standard deviation. So we go this way on the chart, which means we're probably going to land on using the T distribution. So I'm going to show you how to use the T table when we need to be using the T distribution to solve our problems. You'll see that they kind of start out very similar to the types of problems that we did on Tuesday. And the formula even looks really similar. So at some point, you're going to get a formula sheet to use on your midterm number 3. And the formula that we used for confidence intervals on Tuesday, it had this X bar plus or minus Z alpha over 2 times the population standard deviation divided by the square root of the sample size. Today, we're going to be using a very similar looking formula. They both start with the X bar, and then they both have the plus or minus sign. But instead of a Z alpha over 2, we're going to use a T alpha over 2. That just means we're going to be getting the number that we need from the T table instead of the Z table. And then instead of you plugging in the population standard deviation, you're going to plug in the sample standard deviation, and then we still divide by the square root of the sample size. So the formulas are super similar to each other. We just substitute out, instead of the population standard deviation, we use the sample. And then instead of using the Z table, we use the T table to get our number. But everything else about how we're going to solve it is going to be exactly the same. So let's look at an actual example. Says a pharmaceutical company makes tranquilizers. Tranquilizers are things that like lower anxiety, or they make you kind of sleepy. So they could be prescribed for anxiety meds. They could be prescribed for sleep meds. It's assumed that the distribution for the length of time they last is approximately normal. Researchers in a hospital prescribed the drug to a random sample of 9 patients. So when we've done these problems before, we've really wanted to have like 30 or above for our sample size. We got a very small sample size of 9 here. So that's one hint. We're probably ending up over on the T table because our sample size is small. The effective period of the tranquilizer for each patient in hours was 2.7 hours, 2.8 hours, 3 hours, 2.3 hours, 2.3 hours, 2.2 hours, 2.8 hours, 2.1 hours, and 2.4 hours. There's 9 scores there because there's 9 patients. The sample standard deviation is 0.318. I put that on there so you wouldn't have to go calculate the sample standard deviation, because that's a more complicated type of number for you to go find. Not hard, we just would have to do more math. But the first part of the question you should be able to do. So I'm going to give you a second. Find the sample mean for the 9 patients. How do you find a sample mean? Add them all up. Beautiful. Add them all up and divide by how many there are. So I'm going to give you a moment. Add up those 9 numbers: 2.7, 2.8, 3.0, 2.3, 2.3, 2.2, 2.8, 2.1, and 2.4. There's 9 of them up there, so you're going to divide by 9. And we'll see if you got the same number I got.
What do you divide?
You want to divide them by the number of things that you're adding up. There's 9 of them. Anybody get a number? 2.51. Anybody else get 2.51? That's what I got. 2.51. Very good. Okay. So we started by finding the sample mean, and one of the reasons we started by finding the sample mean is that if what we're ultimately going to be looking for is a 95% confidence interval, the very first thing in the confidence interval formula is the sample mean. So we have to have that. In the list of things that we actually were given in this problem, we were given that we have 9 patients. So we got that n is equal to 9 for this problem. And then they also told us the sample standard deviation is 0.318. So they didn't give us a sigma, they gave us an S is equal to 0.318. But they didn't give us the sample mean, so we had to go find that. So that was step 1. Step 2 says, what are the degrees of freedom for this problem? When she was talking about degrees of freedom, did she give you a formula for degrees of freedom? Should have been a pretty simple formula. It would have involved n. N minus 1. Okay, so when you want to find degrees of freedom and we're using the T table, degrees of freedom are equal to n minus 1. And in this case, our n was equal to 9. So we're going to do 9 minus 1. And so your degrees of freedom are 8. You will do other kinds of problems that will talk about degrees of freedom, and you'll have different formulas for them. So degrees of freedom for doing this particular type of problem where we find a single population mean, we do n minus 1. But sometimes they'll ask you for degrees of freedom for other types of problems. So that'll be one of the things when people are like, so what gets complicated about the last part of statistics, Jen? And I'm like, same thing that was complicated before, making sure we use the correct formulas for the correct types of problems. We have to be able to match things up to know what the formula sheet is helping us do. Okay. Last thing says, construct a 95% confidence interval for the population mean length of time that the tranquilizer lasts. Okay, so our formula looks really similar to the formula that we used on Tuesday. Still got an X bar. Still has a plus or minus sign, but now instead of writing a Z alpha over 2, we're going to write a T alpha over 2, which is telling us we're going to use a different table. And then we're going to multiply by the sample standard deviation divided by the square root of n. So very similar, but slightly different formula than we used last time. So we have our X bar, you guys just found that, it was 2.51. We have the S, that's 0.318. We have square root of n, that's going to be a square root of 9. That'll be easy. So the thing we don't have yet is the T alpha over 2. So we need to use that T table that we got. And the degrees of freedom on the T table are in this first column right here. So when we figured out that the degrees of freedom is 8, then that tells us that we're going to be coming across like this to go find the number that we need for our T alpha over 2. Where we're going depends on what size confidence interval they've asked us for. They asked for a 95% confidence interval. So that means that 95% of the data is in the middle of the table, which means that 2.5% is in this tail and 2.5% is in this tail. And so we labeled last time that that means that this bar right here is the number 0.025. And then this one right here is the number 0.975. So let's take a look at the t-table to figure out where we're going. Okay. So we figured out, let me zoom in. We figured out that we're at degrees of freedom 8. So I'm going to put a piece of paper under 8 here. Okay. And then now we got to figure out which column we're in. So we're trying to do a 95% confidence interval, which means that in the two tails combined, we have 5% left of the data. So for the two-tail part of it, you're looking for 5%. 5% as a decimal is 0.05. But that means if we're talking about just one tail, that's the alpha over 2 part. You're cutting that in half, so that would be 0.025. Or another way, depending on how the table's lined up, they might say that it's the t value for the 0.975 number, which I just labeled on the graph, that we had 0.025 on the one side and 0.975 on the other side. So I don't know specifically what your table says, but someone showed me at the end of class last time that it at least had the one tail and the two tail part. So we know that in the two tails combined, we have 5%. So that means that we're in this column right here. And so the number that we want for T alpha over 2 is 2.306. 2.306. So after the plus or minus sign, we're plugging in 2.306. My X bar you guys found for me was 2.51, so I'll put that first. And then we're multiplying by the S, which is 0.318. And we're dividing by the square root of n. N is 9. So 2.51 plus or minus, if I multiply out this next part, that's called the error bound measure, the EBM. So I'm going to take the 0.318, divide it by the square root of 9, which is just 3. And then I'm going to multiply that number by 2.306. So that means that my error bound measure is 0.244 if I round it. So what we're going to do is one time we're going to take 2.51 and we're going to subtract 0.244. That's going to give us the lower number. And then one time we're going to take 2.51 and we're going to add 0.244. That's going to give us the higher number. And so we write that in parentheses like this. We put the smaller number here and the bigger number here. So I'm going to do 2.51 minus 0.244. And I get 2.27 if I round it to 2 decimal places. And then I'm going to take 2.51 again, and this time I'm going to add 0.244. And I get 2.75 if I round it to 2 decimal places. Question? This was from last time, and I had the packets there. Apparently everyone took them. Did anybody get an extra one, like they actually got one last time and they didn't need to grab the one when they came in today? Thank you, thank you. Okay, It doesn't say to do this, but we should do it anyway. We wrote the confidence interval, but the confidence interval is just numbers right now. Let's write out what it means. So I could have said interpret the confidence interval. So let's say this was a 95% confidence interval. So I'm going to say we are 95% confident that the true mean length of time the tranquilizer lasts is between 2.27 and 2.75 hours. Because the unit they were using in this problem was hours. So once you get the confidence interval, we want to actually know like, okay, but what does that mean in terms of this problem? So we're 95% confident that the true mean length of time the tranquilizer lasts is between 2.27 and 2.75 hours. So that is not to say that 100% certain that that's how long it's going to last, but we're pretty darn certain. 95% confidence, pretty good. If we wanted to be more confident that we got the right amount of time the tranquilizer lasts, we could do like a 98% confidence interval. But whenever we make it a wider confidence interval, we're being less specific about how long it lasts. So if I wanted to be more sure, I'd have to widen the confidence interval. So I might be saying it's between 2 hours and 3 hours now, which is not as specific, but I'm more confident that I'm right. So we always have that trade-off when we're doing confidence intervals between being specific about the answer and being sure that our answer is contained in the interval. Okay. So this process, super similar to what we did on Tuesday, but there were two changes. One of the changes was we needed to use the t table to get this number instead of the z table to get this number. And this one, whenever it's a t, we got to use the degrees of freedom, and we didn't have to do degrees of freedom on Tuesday. And then the other change was we didn't get a sigma, we got an s in this problem. So we have a sample standard deviation. Question?
I don't know if you like went over this before I walked in since I was a couple of minutes late, but I was just kind of wondering how you could tell the difference if you're supposed to use a T chart or if you're supposed to use a chart.
Good question. Okay, let's go back and see what our hint was. Don't look all the way at the top because the hint is in the title here where I'm like using the t distribution. Don't go that far. Go here. All right. One of the big hints was that it said that we only sampled 9 patients. That's not very many. So whenever there's not very many, I get really suspicious it's going to be a T. But we don't know for sure certain just because it's not very many. It could be that we can't do this problem. So what we're looking at is that chart that we got last time. And in the chart, the first thing that we're asked in the chart is, did we get the population standard deviation? And then in this problem, we did not get the population standard deviation. We only got the sample standard deviation. If you do get the population standard deviation, you go this way, and ultimately this side ends up on the Z's. If we don't, we end up this way, and ultimately this side usually ends up in the T's. But what was a particularly important line in the problem, it said that we were still pretty sure that this data was normally distributed. So after we came this direction, it said, is the population normally distributed? And we're like, yeah. And then we got to come down here and use the t. If we had said, no, it wasn't, then we would have needed our n to be bigger than 30 again. So it was okay we only had 9, because we knew that the population that it was coming from was approximately normally distributed. So that's important. Good question. Okay. We're going to do another one that's not broken down step by step. So it looks kind of more like how problems are normally going to be given to you in this section. Okay. Suppose that 14 children who were learning to ride two-wheel bicycles were surveyed to determine how long they had to use training wheels while they were learning. Okay, as soon as I saw 14, I went, ooh, that's not very many. I'm guessing it's probably going to be a T. But I'm hoping in here it says something about being normally distributed, or I might be a little nervous. So it says, it was revealed that they used them for an average of 6 months with a sample standard deviation of 3 months. So I got a sample standard deviation, not a population standard deviation. So I'm again going probably T now. Assume that the underlying population is normal. Sweet. I have all the things that I need that's going to let me go do this as a T distribution problem now. Construct a 99% confidence interval for the mean length of time using training wheels. So they want to be like really certain if they're saying a 99% confidence interval. So that means it's going to be a wide confidence interval, but it means that it's going to be maybe like not a particularly helpful number in the end, because you're going to go, well, it's kind of wide. Like that's a long range there. That's okay. We're going to do what they asked. So first thing, when I see 14 children, I know that our N is 14 for this problem. And they said it was revealed that these 14 children who were the sample, used them for an average of 6 months. So because this was for a sample, that's our X bar is equal to 6 months. And then they said we had a sample standard deviation of 3 months. So that's going to be S is equal to 3. All right. The other thing they told us is that we're doing a 99% confidence interval. So that means that the alpha is 1%, which we write as a decimal 0.01. So because it's a 99% confidence interval, that means that we have 1% for the alpha. And then we always write the 1% as its decimal form. So we move the decimal point over 2 places. So your alpha is 0.01. If your alpha is 0.01, you have 99% of your data in the middle, which means you have 0.5% of your data in each tail, because 0.5% plus another 0.5% adds up to that 1% that's left over. So the two numbers that are at the lines, we have to move that decimal point over 2 places. So this would be 0.005 at that first bar. And this one would be 0.995. Or if you weren't sure how to do that, you'd do 1 minus this number, and I'll give you the other number. Okay. One more thing they didn't give us, but that isn't too hard to find out. I need the degrees of freedom because we said this is a T distribution problem. What's my degrees of freedom going to be? 13, because it's going to be N minus 1. So we're going to do 14 minus 1, which is 13. Beautiful. All right, I now have everything I need to go figure out the T alpha over 2 value that comes from the T table. So T alpha over 2. What I'm going to do is go down to degrees of freedom 13. So degrees of freedom 13 is right here. Cool. And then now, if it's a 99% confidence interval, that means in the two tails, there's 1% left. So 1% is 0.01, so you're coming over here. If you're looking at the two tail part of it, that's the combined amount. In one tail, there's half of that. So the 0.01 gets cut in half, and that's 0.005. So on the table, you can either tell yourself, okay, how much do I have in two tails and go find that number, or figure out how much you have in one tail and go find that number. It's going to put you in the same column. So you don't have to do both. I'm just doing both so that it's however your brain likes to hear that most. So I often think about how much is in two tails because that's like an easier number for me. If I was like, it's a 99% confidence interval, then there's 1% in the tails. 1% is 0.01. Cool, I'm in that column. So that means I'm coming down here and the number I want is 3.012. 3.012. Okay. Now we're just using our formula. So our formula is X bar plus or minus the T alpha over 2 value times the sample standard deviation divided by the square root of the sample size. And we have all those numbers now, so we're just plugging them in. So our X bar we said was 6 plus or minus. The T alpha over 2 we said is 3.012. The S was 3. And we're dividing by the square root of n. N was 14. Cool. Okay. So 6 plus or minus, if I do this calculation, that's the error bound measurement. So I'm going to do 3 divided by the square root of 14. And then I'm going to multiply that number by 3.012. Okay. So 3 divided by square root of 14. And so that comes out to be 2.415 if I round it. So my error bound 2.415. So one of the times I'm going to take 6 and subtract 2.415, and one of the times I'm going to take 6 and add 2.415, and then that's going to give me my numbers inside the parentheses. So we're going to do the smaller number first. So 6 minus 2.415 is 3.59 if I round it to 2 decimal places. And then the second time I'm going to do 6 plus 2.415. And I get 8.42 if I round it. So it didn't ask us to do the interpretation part, but I still think it's good for us to do it. So I'm going to write it out in words in there. This is a 99% confidence interval. So I'm going to say we are 99% confident that the true mean length of time using training wheels is between 3.59 and 8.42 The unit on this one was months. So we said that the average length of time that these students use training wheels, children, was 6 months. So we're 95% confident that if I were to ask a whole population of children in this age group, that the true mean length of time would be between 3.59 and 8.42 months. That's a pretty wide interval if we were saying 6 months for the sample. And so the reason it's so wide is that we were trying to be really, really sure, and we used a 99% confidence interval. But like if you were a researcher and you were like, that's not close enough, I need it to be a smaller range, then you would need to be less confident. So you'd have to change it to be like a 95% confidence interval, and then you might get a more useful number. So as a researcher, you're always making that trade-off between, do I want to be really confident? But if I'm really, really confident, sometimes my number is not as helpful. If I want a more helpful number, I have to be a little bit more okay with being wrong. Questions on that part? Which one do you like better? Do you like Z's or T's? They're not really all that different, but the tables are, you have to know different things to read the table. And so that's what gets to be a little confusing for people. So that degrees of freedom thing, you can't forget if it's a T test that we're going to have to actually like, oh yeah, I got to go calculate degrees of freedom. But if we're actually like in the problem, they're talking about degrees of freedom, you already know, well, it can't be the Z table. We don't do any degrees of freedom on the Z table. So sometimes it's a hint. Okay. I don't know for certain what she's going to do as your next topic, but usually the next topic that's either the very next topic or is coming next week is hypothesis testing. So I made a handout on hypothesis testing. If I'm wrong, then you'll definitely have it the following week, but I'm pretty sure it'll be the next thing you're talking about. Were you asking for the sign-in sheet?
Yeah.
This way.
Thank you.
Okay. Have you heard of the word hypothesis before today? All right, just not in a statistical context. Okay. Hypothesis testing is actually like one of the biggest reasons why you're taking statistics in the first place. Like, it's kind of like we've been leading up to getting to do hypothesis testing. Let me show you her formula sheet again that you're going to probably, I assume this is going to be the same formula sheet for her midterm 3. Maybe not. She might make it look different, but this was the midterm 3 formula sheet for the last time she taught. So I was just going through the confidence interval stuff with you guys. We were doing the Z confidence interval and the T confidence interval. But if you come across this way, the first part here, she's actually got hypothesis testing stuff in the first part of it. So it kind of all goes together. So like what you were doing was starting with confidence intervals, but now we're working our way over to this idea of what a hypothesis is. So in terms of like how I think of a hypothesis, basically, as statisticians or researchers, we're interested in something being weird. Like when you're doing studies on things, it's not particularly like interesting to have a study where you're like, teenagers like to sleep in. Let's test that. Yes, they do. Like, duh, that's not like an interesting study, right? But if you did a study and you were like, actually, 95% of teenagers like waking up before 5 a.m. And be like, whoa, what? Like, I want to read that study because that's weird. So when we do research, like, we want to hear something cool. We want to hear something different. We don't want to hear something that we assume to already be true. The thing that we assume to already be true, we often call the null hypothesis. The null hypothesis is like boring, or they'll usually use the word status quo. That sounds way more technical and more like academic than Jen saying boring, but usually we say the null hypothesis is the status quo, but it really means it's the boring thing. It's the thing we already assume. And so we actually hope, usually as researchers, that we have some evidence to reject the null hypothesis. We want to be able to say that boring thing is not actually what's happening because it lets us publish research papers that people want to read. People don't want to read research papers that are like, teenagers like to sleep in. That doesn't give us any new information. They want to read something that they're like, what? Why do you know that? That's the thing that is actually going to be like more popular. So when we are doing hypothesis testing, often what we're having to do is look at a scenario and figure out what's the null hypothesis. And then the other thing we are looking for is the interesting thing is the alternative hypothesis. So I have some scenarios here where we're going to try and figure out what's the null hypothesis, what's the alternative hypothesis. One of the things we need to first learn is notation. It's really kind of bizarre notation, but when we're talking about null hypothesis, what we do is we write an H and we put a little 0 after it. This 0 is called the null. Null stands for like nothing. So 0 is technically nothing. So I guess it makes sense when you think about it that way. So if they write an H with a 0, that means we're talking about the null hypothesis. And if I write the H with an A after it, that's the alternative hypothesis. Sometimes they'll write a capital A instead of a lowercase a. Like actually most of the time, I think you'll see a capital A, but it's okay to write a lowercase a. Doesn't change it. The null hypothesis, one of the important things to keep in mind is that typically speaking, it's going to have an equal sign in it somehow. So the null hypothesis could have just a straight up equal sign in it, or it could have a greater than or equal to sign, or it could have a less than or equal to sign. But the null hypothesis should have the equal sign in it somewhere. So either an equals on its own, or a greater than or equal to, or a less than or equal to. The alternative hypothesis is either going to have a not equal to sign, or it'll have a less than sign or a greater than sign. So one of the homework questions that comes up from time to time is the null hypothesis always has an equal sign. Yes, that's true. The null hypothesis is always going to have an equal sign. And people go, but it's a greater than or equal to sign. That's okay. They just mean that the equal sign is in there somewhere. If the equals is attached to the greater than, that's okay. Okay. So there's this idea of having a statement, and there's an idea of having the hypothesis. And so sometimes the statement and the hypothesis are like the same thing, and sometimes the statement and the hypothesis are like going to be opposites of each other. It's kind of hard to like explain that without looking at examples. So we're just going to start looking at examples and we'll talk through how that looks. Okay. So this right here, the top one, A, let me put a piece of paper under it so we're not staring at as many things all at once. All right. The mean number of years Americans work before retiring is 34 years. Okay. So this is a statement. The statement is saying that this is what the mean is. Okay. When we want to turn it into a hypothesis, what we have to do is set up something that we can either prove or disprove. Now, the truth is, when we do hypothesis testing in statistics, we never get to prove that the null hypothesis is true or the null hypothesis is false. We only get to say that we accept the null hypothesis is true, or we reject the null hypothesis, but we can't actually prove it. So that's a little bit like weird of a concept, but it's sort of that idea that like in science, we can find evidence for things. And so if we find evidence that allows us to reject the null hypothesis, we're saying the evidence says it's probably not true, but we can't prove it's not true. Or if we decide to accept the null hypothesis, that means that we don't have enough evidence to say that it isn't true. So in this case, the thing that we're looking for evidence for is the mean number of years Americans work before retiring is 34. We're just making a statement. So the boring statement would be that this is true. So our null hypothesis in this case is going to be H with the little zero, null hypothesis. How you'll sometimes hear people read this is H naught. H naught. And when I say not, N-A-U-G-H-T is how we spell that word. H naught. It means zero. So our null hypothesis is that H naught here, we're talking about the mean. And whenever we're doing these types of hypothesis tests, we're talking about the population mean. So we're going to use the symbol for the population mean, which is the mu. And the boring thing would be if we just said this statement's true. They're saying that the mean number of years Americans work before retiring is 34. So we're saying that the mean is equal to 34. That's the boring thing. That's our H naught. So our alternative hypothesis then is our HA. You can use a capital A or a lowercase a. I'm going to use a capital A. Our HA is that the mu is different than what this statement says. The mean number of years Americans work, maybe I think it would be interesting to be like, no, it's not. They're telling me it is, but I discovered evidence that it's not. And so what we would put is a not equal to sign and a 34. So if in general what we believe to be true is that people work for a mean amount of time of 34 years, and you actually do a study and you find out that actually no, after the pandemic, a lot of people's savings got wiped out, and so they're actually working more like 38 to 40 years now, that would be an interesting paper to write. I'd go, oh, really? It was different before then, and now it's changed because of things that have happened in like globally, like whoa, or now we have tariffs and people can't retire, so they're working a lot longer. Like, oh, that would be interesting to read. So what you would be doing when you're setting up a research study, your null hypothesis is that it's exactly what it's always been. It's boring. It's 34 years. What would be interesting would be the alternative hypothesis being true. So what you do is you test the null hypothesis and you try and find evidence that says, oh, actually the null hypothesis doesn't appear to be true. Do we have enough evidence to reject the null hypothesis? If so, we get to say it's not 34 years. Now, if I say it's not 34 years, could it be 33 years? Yeah, not 34 years could actually be people are working less amount of time. Or it could it be 38 years? Yeah, that's not 34 years either. So what we don't know when you have a null hypothesis that just has an equal sign, if the alternative is that it's just not that, you don't know if it's higher or lower. So we call it a two-tailed test because it could be higher or it could be lower. So we got to check when we do the distribution, you have your lower numbers on one side, you have your higher numbers on the other side. We got to check both of them. So it's called the two-tailed hypothesis test, but it's got an equal sign for the null hypothesis and a not equal sign for the alternative hypothesis. So I'll see if I'm going to put that over here, two-tail test. All right, let's look at the next one. At most, 60% of Americans vote in presidential elections. This is a statement. It's not a hypothesis, it's a statement. It says, at most, 60% of Americans vote in presidential elections. And so, what would be boring is if the statement is true. What would be interesting is if the statement is false. So, our null hypothesis is going to be for us to write exactly what it says. So our null hypothesis, how do I write that at most 60% of Americans vote in presidential elections? That's not a mean, it's a proportion. So we're not going to use the mu symbol for this one because we're not talking about a mean, we're talking about a proportion. So we're going to write P. And if we say at most, does that mean it could be bigger? No, it means it could be smaller. So at most means you're going to put a less than sign. But whenever we're doing a null hypothesis, you have to have the equal sign in there. So you're going to put a less than or equal to. You're going to put the little line underneath it. You always have to have an equal sign when you're doing your null hypothesis. Okay? So we would say that P is less than or equal to, and you can write 60%, but I'm going to write it as a decimal because we normally see the proportions as a decimal. So I'm going to say 0.60. That's our null. So our alternative hypothesis has to be the opposite of this. So my HA would be that my P is greater than 60%, so 0.60. So in this case, if I said that this was, I had evidence to say that this isn't true, and if we rejected the null hypothesis, we're actually saying, oh, we think the proportion is higher. Not higher or lower, specifically higher. And so that means it's a one-tail test. Okay. The mean starting salary for San Jose State University graduates is at least $100,000 per year. Whoa. Whoa. Okay. Didn't leave enough room on the paper like right there for us to do it, but that's okay. The mean. So I'm going to use the P or am I going to use the mu? The mu. So your H naught is going to start with the mu symbol. Okay. This time it says at least 100,000. So could it be lower than 100,000? At least 100,000? Could you make 90,000? If I'm saying you make at least 100,000, can you make 90,000? No. So it has to be greater than. So you're going to write greater than. And we always have to have the equal sign in the null hypothesis. You're going to put the line underneath it. Greater than or equal to 100,000. So your mu for this one. I can't put it on the paper where I want to put it. I'll come down this way. Okay. So that means that your alternative hypothesis has to be the opposite of that. So you're going to write that the mu is less than 100,000. So would you say this is a one-tail test or a two-tail test? What do we think? The reason it's a one-tail test is that if it turns out that this one, we don't have evidence to support it, then I'm saying, well, specifically then the mean is less than 100,000. So we're only looking on one side of the distribution. We're not saying that it could be less than 100,000 or more than 100,000. We're just saying it's on the one side. So this is a one-tail test. Okay. Let's look at D. 29% of high school seniors get drunk each month. Ugh. I don't know. I was a high school teacher. I hope this isn't true, but if that's the statement that they're making, then we would be saying that's the null hypothesis here. So 29% of high school seniors get drunk each month. Then what I'm setting up, so wait, this one was C, this one's D. It's a percent. So we're not talking about a mean, we're talking about a proportion. So you're going to use a P. And I'm not saying 29% or more. I'm not saying 29% or less. I'm saying exactly 29% of high school seniors get drunk each month. So you're going to put an equal to sign and put 0.29 there. Now, I personally hope that's a high number. So I'm hoping that I go do a study that suggests it's not 29%, it's actually less than 29%. But I am also really naive. I didn't drink in high school, so I just assumed most people didn't drink in high school, but my friends tell me otherwise. It's also entirely possible it's like 33%. You know, it could be higher. So because it could be lower, Jen could be right, or it could be higher, Jen could be wrong. This is a two-tailed test because we could get numbers on either side. So this one's two-tailed. So when you do your alternative hypothesis, your HA has to account for the fact that it could be either one. So you just put a not equal to sign. So it's not equal to 29%, which means it could be less than 29% or it could be greater than 29%. We call this a two-tailed test. Let's do one more. These get pretty boring after a while. I don't want to like make you go through the whole list, but let's do one more. Fewer than 5% of adults ride the bus to work in Los Angeles. So fewer means it could be 4% or it could be 3%, but it can't be higher. So we would say less than. But here's the problem. Fewer, I guess I shouldn't take that paper away yet. Let's look at it again. If I want to make my null hypothesis, the rule is the equal sign has to be with the null hypothesis. And so if I say that fewer than 5% of adults that's fewer. It doesn't say at most. If it said at most, it would have the equal sign, but it says fewer. So it's saying not 5%, definitely less than 5%. I have a problem because I have to have the equal sign there. So in this case, I actually can't put this one as the null hypothesis. And so this is where sometimes she'll give you some questions and she'll say, is the hypothesis, the null hypothesis, the same as the statement. In the ones that we've done so far, the null hypothesis was exactly the same as the statement for all of them, but this one is not the case. So what I have to do is I have to strike this balance of the thing that is my alternative hypothesis and the thing that is my null hypothesis. So what we're going to write on this one is that the alternative hypothesis is actually that it's less than. And so the thing that would have the equal to sign would be the opposite of this thing. That'd be the greater than or equal to. That one has to be your null hypothesis. So for us, I'm going to write down the alternative hypothesis first because that's the part that made sense. We said that it has to be fewer than 5%, 0.05. But because it has to have just the less than sign, then on this side has to be where the equal sign goes. And so it has to be the opposite of whatever that sign was that we wrote. It's got to be a greater than sign, and it has to include the equal sign. So we put the equal underneath it. Okay. That feels really scary and tricky and all of the things. It doesn't really come up that often on her stuff. So I don't want you to be like, I would totally miss that. It's not really, she doesn't do a whole lot of it, but there is, what does come up a lot is the equal sign has to be with the null hypothesis. Yes. I'll post the solutions for the other ones in Canvas. So if you decide you want to go do the other ones later, you can sort of check yourself and see if you get the same answers. But I'm gonna leave those for now so that you're not like, ugh, that's super boring. Let's actually take a look at some hypothesis testing issues. So if you flip that paper over, one of the issues that we have to think about is error. Error comes up in hypothesis testing all the time. And we already kind of alluded to this idea of error when we were talking about the confidence intervals, and that we have to sort of make a trade-off between how specific we can be with the number with how confident we want to be with our results. When we're doing hypothesis testing, these errors have special names. They're not very descriptive names. Type 1 errors and type 2 errors. A type 1 error occurs when we reject the null hypothesis when it turns out it's actually true. So if we went through one of our examples that we just did, so we said that the null hypothesis for the mean number of years Americans work before retiring is 34. So we said the null hypothesis was that the mean is exactly 34 years. If we rejected the null hypothesis, we'd be saying, oh, we have evidence that it's different than 34 years. But it might turn out that the evidence that we got is actually not accurate. And so if we rejected the null hypothesis when it's actually true, we've committed what we call a type 1 error. A type 2 error is when we fail to reject the null hypothesis when it's actually false. So if we go back to that same example, if we said the mean number of years that people work before retiring is 34, and we say we don't have enough evidence to say that's not true, so we're just going to say we think the mean number of years is 34, but it is actually the case that people are working way more than that, but the evidence that we came up with just didn't show that, then we'd be committing what we call a type 2 error. So those are confusing. They're very confusing. People mix them up all the time. So I have some examples to go through, and we'll try and look at them and figure out what would be an example of a type 1 error in each situation or an example of a type 2 error in each situation. So it says, consider the following scenario where we're planning to go climbing utilizing climbing equipment. Do they still have rock climbing over in the Ark? Here's our null hypothesis, and I'm going to guess this is the null hypothesis that everybody has when they go over to the ARC. The climbing equipment is safe. We would like that to be the case. We want that to be the boring situation. Yes, the climbing equipment is safe. Okay. What would it mean for us to commit a type 1 error in this situation? So a type 1 error, remember, is we reject the null hypothesis when it's actually true. If we rejected this, what does it mean to reject this? That it's not safe. So we'd be saying that the climbing equipment is not safe. So that's the first part. It says this occurs when we reject the null hypothesis. Okay, so we're saying the climbing equipment is not safe. When it's actually true. So we said the climbing equipment is not safe, but it actually is safe. That's what it would mean for us to commit a type 1 error. So we would say we said that the climbing equipment is safe. Or sorry, we said the climbing equipment is not safe. When it's actually safe. Is that a particularly big deal? So you go over to the ARC and somebody is looking at the climbing equipment and they go, no, it's not safe. Turns out you would have been fine. Nothing would have happened to you. But they decide not to let you climb because they decided it wasn't safe, even though it actually was. Is that a big deal? It's a bummer, but you ain't going to die because of that decision, right? So in this case, a type 1 error is not the end of the world. So we might be okay with committing a type 1 error for this particular research study if we were, conducting a research study and we decided, I'm going to say it's not safe. It doesn't have earth-shattering consequences as a result. Let's see what it means to commit a type 2 error here. Type 2 error means we fail to reject the null hypothesis. So if we fail to reject the null hypothesis, that means that we keep it the same as it is. So we say the climbing equipment is safe when it's actually false. We say the climbing equipment is safe when it's actually unsafe, is what this means. Are you cool with committing a type 2 error? No, this one is bad. If you're wrong on this one, someone could die or at least get really hurt. So when you're doing research studies, we're balancing out our willingness to commit a type 1 error versus a type 2 error, because here's the problem. If you decrease the chance of making a type 1 error, then you actually increase the chance of making a type 2 error and vice versa. So we have to make a balance between the two when we're doing statistical studies. In this case, I'd be really okay with making a type 1 error. I'm really not okay with making a type 2 error. So if I have to increase the chances of me making any particular type of error, I'm going to say, well, I'm way more okay to make a type 1 error in this case. But in some cases, you'll be way more okay to make the other type of error. It just depends on the circumstance. So that's why we kind of need to talk about what a type 1 and type 2 error are. Okay, I think we got time to do one more. All right. Consider the following scenario about a fire alarm system sounding an alarm or not. Okay, so there's a fire alarm system and the null hypothesis is there is no fire. Okay. So alarm is going off and there is no fire. All right. So in this case, type 1 error is this occurs when we reject the null hypothesis when it's actually true. So if we've rejected the null hypothesis, we say there is a fire. But it's actually true that there is no fire. Okay, so we've rejected this, but it's actually true. So what we would say here is that the fire alarm goes off, but there is no fire. Okay, are we super concerned about this? No, it's probably happened to you at some point in your life where a fire alarm has gone off and you've evacuated a building and then they're like, oh, it's a false alarm. You're like, oh, it's not the end of the world. No one dies. It's annoying, but it's not the end of the world. What would it mean to commit a type 2 error in this situation? A type 2 error is we fail to reject the null hypothesis. So we fail to reject it. So we say that there is no fire. When it's actually false, there actually is a fire. So in this case, there is a fire. But the alarm doesn't go off. Again, that's a problem. So we'd be way more okay with committing a type 1 error in this situation and way less okay of committing a type 2 error in this situation. So that could be dangerous. All right, the next thing that I was gonna jump into is actually doing hypothesis testing, but that takes lots of time. So I figure I'm gonna stop here and then we'll pick up with the actual hypothesis testing next time, unless you guys go over something completely different and then someone send me an email so I know that, or put it on the discussion board and I'll go over whatever you actually went over, okay? All right, have a good weekend, guys.